Lesson 10.1, Exponential Functions. This part was meant to basically give you a quick overview with examples of how exponential functions are and what they look like and the form they take. So basically, we are talking about exponential functions that are of the form y equals abx, or excuse me, ab to the x power, and the a represents the initial amount, b is going to be either exponential growth or decay, and based upon that, if it's greater than 1, it's going to be exponential growth. If it is between 0 and 1, it's going to be exponential decay. And this graph shows you what it looks like. Okay, where you have your x-axis is basically a horizontal asymptote. When x is 0, you have y of 1. Okay, and that basically means down here that your y-intercept tells you the a value. It's 1 to 1, it's a function. The domain is also real numbers, and so on. Now, we're not going to do a lot more with that, but that's some basic rough ideas. Like I said, if it's below 1 and between 1 and 0, you have exponential decay. If it's greater than 1, it is growth. Growth. This example is one of how to come up with the equation of y equals ab to the x given coordinates. Now, this is the word problem, but it's still coordinates. And the coordinates for this particular example are that in 1983, they had 102,000 farms. I put a 0 here because this function is going to be with respect to years since 1983. So our first point of data is going to be 1983, but that's considered 0. And at that time, there's 102,000 farms. And then in 1998, which is 15 years later, they had 80,000. So these are our two coordinates. Again, this is a word problem, but in its essence, these are the two coordinates that we use. Now, like we said, this represents the a value of our formula. Okay, so we would put in 102,000 for A, and then we would need to find out what B is to have the equation. And that's where this comes in. So we know we have 80,000 farms when it's 15 years later. So we divide by 102,000 rather. And b to the 15th equals, I believe, 0.78. And then you take the 15th root of that. And the 15th root of that is I believe they have 0.98. Yep. So our final equation would be y equals 102,000 times 0.98 to the x power. And that's what you do with two coordinates. Now we're going to talk about logarithms a lot, and we have to understand exponents then before we get too involved with it. So a couple of brief rules are that if the bases are the same and you're multiplying them, the exponents are added. If you have a power raised to a power, they are multiplied. There's some quick review here. But then we're going to get into some basic ideas which might seem obvious at first, but they are very important. And that is that if you have this statement where the bases are the same, then in looking at the equality, one would say that, well, x has to be 8. So what happens is you can ignore the bases and you get just the equation x equals 8 to solve. And that's important because it allows us to solve for a variable even if it's in the exponent position. Here's a good example where they have 3 of the n, 2n plus 1 equals 81. As is, it doesn't help us at all. But if we change 81 to something with a base of 3 to a power, we can go further. So they choose 3 to the 4th. 3 to the 4th is 81, but notice they both have the same base, which allows us to ignore them and go with just the exponent equation. And we can solve that for n. And here's a situation where they have two changes that need to take place. You can't write 8 as 4 to some power, but you can write 8 as 2 to some power. And 4 can be written as 2 to some power. So in this situation, we have a power raised to the 2x, which is still there. So 2 raised to a power of 2x gets multiplied. So we have 4x. Here we have x minus 1, so it's 3 times x minus 1, parentheses. Again, the bases are the same, so we can ignore them and go right to the powers and say 4x equals 3 parentheses x minus 1 and solve for x. Inequalities are also important to understand. Does that work with inequalities? Well, here we have a situation where the bases are the same, so you just ignore the bases and look right to the powers, and you have x is less than 4, so they do hold for inequalities as well. This is a good example where we have a fraction. Well, 256 is the same as 4 to the 4th power. But we want to write that in non-fraction form, so if we bring it up here, the power becomes negative. And that's where we get this from. So again, we have bases that are the same, so we can go right to the inequality and solve that inequality. We'd have to check that to make sure it works, and that's what they do in the end statements here. That ends lesson 10.1, and thank you.